In this video, we're going to discuss a different type of series called a power series, as well as the MacLaurin and Taylor series. So first, let's define what a power series is. A power series is a series of the form sum from 0 to infinity of Cn x to the n. And the important part here is we have an x in this series. It's not just a list of terms like what we had before being added up together, but we also have a variable x. So before we always had that a series either converged or it diverged, and that was it. But now having this variable in the problem, it could converge for some values of x and diverge for other values of x. So we're going to have to figure out when these different types of power series converge or diverge. And it does not have to just be some constants times x to the n. We can also have it a little bit shifted like this. A series of the form sum from 0 to infinity, Cn times x minus a to the n is a power series. In x minus a, or sometimes we say centered at a, or sometimes we say it's a power series about a. All of those mean the exact same thing. It's still a power series because we have a variable x. We're just shifting it slightly. So one thing that we should note is that all of our power series are going to converge for at least one value of x, and that's the value which makes the whole power series equal to a sum of zeros. So when it's in this form with an x minus a to the n, this power series is definitely going to converge when x equals a. Because when x equals a, this just becomes a sum of zeros. And 0 added together infinitely many times is still 0. And when it doesn't have this minus a shifting it, and it's just an x to the n, that series is going to converge when x is 0. So there's always at least one point which makes the power series converge. But it's not always just one point. It can be many different points. So let's do an example where we try to find where a certain power series converges and where it diverges. So for what values of x is the series the sum from 0 to infinity of n factorial times x to the n, when is this convergent? And the standard way to figure out where a power series is convergent or divergent is to use our ratio test. Remember, the ratio test says that if you look at the ratio of an plus 1 to an, take a limit, if that happens to be less than 1, well, then you have convergence. And if it's greater than 1, you have divergence. Equal to 1, we don't know. And when we're using this ratio test to figure out if a power series converges or diverges, let's use the version that uses the absolute value bars. So the ratio test for absolute convergence. So by my ratio test, I'm going to look at the limit as n goes to infinity of an plus 1 over an in absolute values. And for this particular problem, I have an n plus 1 factorial, x to the n plus 1, n plus 1 factorial, x to the n plus 1, divided by n factorial, x to the n. Now, if I try to simplify this, we already know the n plus 1 factorial and the n factorial, most of that cancels out. just leaves an n plus 1 in the numerator. And same with my x's. I can cancel out most of those x's and just have an x left in the numerator. So this is the limit as n goes to infinity, absolute value of n plus 1 times x. And now let's think for a second. N plus 1. Well, n plus 1 is going to be something positive because my n started at 0 and went up to infinity. So no matter what, n plus 1 is positive, so I don't really need the absolute values there. This x can be anything, so it needs absolute values. But since that x does not involve n, I can pull it out of the limit. So I get absolute value of x outside of the limit, and then I can do the limit as n approaches infinity of n plus 1. Well, that limit is equal to infinity, even when multiplied by my absolute value of x. So this is just going to be infinite. Now, remember, the ratio test says we converge when we're less than 1. Well, I got an infinite limit, so this diverges. Except when x is equal to 0. Because remember, our power series always converge at least one point, and when x is equal to 0, my original series is just the sum of zeros, so it converges. Let's do another example doing this. So our next example, for what values of x does the series, the sum from 1 to infinity of x minus 3 to the n divided by n converge? And again, we're going to use that ratio test for absolute convergence to figure this out. So we're going to look at the limit as n goes to infinity of absolute value an plus 1 over an. That gives me a limit as n goes to infinity of absolute value x minus 3 to the n plus 1 over n plus 1. And when I divide by the an, I'm going to write that as multiplying by the reciprocal. So I get an n over x minus 3 to the n. Now let's simplify as much as we can. Again, I can simplify some of these x minus 3's. I will have just a single x minus 3 left on the top. Since the x minus 3's then no longer involve n, I can pull that out in front of the limit. It needs to stay inside of absolute values because we don't know what x is yet. And then I have a limit as n goes to infinity of n over n plus 1. I don't need absolute values on that n over n plus 1 anymore because my n's are all positive. So now when I take this limit is equal to 1, and I still have it multiplied by x minus 3. So the entire thing is equal to absolute value of x minus 3. So when does this converge and when does it diverge? We have to remember what the ratio test tells us. This is going to converge when this limit is less than 1. So what I want is x minus 3 in absolute values to be less than 1. And then I just have to solve that inequality, and it will tell me the x's for which this series converges. So if I'm solving this absolute value inequality, I can write it as -1 is less than x minus 3, which is less than 1, and add 3 to everything, and I'm going to get 2 is less than x is less than 4. So I know for sure that as long as x is between 2 and 4, my series is going to converge. What I don't know is what happens at 2 and at 4. If I had x equals 2 or x equals 4, my ratio test would give me a limit of 1. And we know that a limit of 1 is inconclusive. So we have to check those endpoints, 2 and 4, separately with a different sort of test. So now let's check our endpoints. X equals 2 and 4. For x equals 2, we'll just plug the 2 into the original series. My series would then look like the sum from 1 to infinity of my x minus 3 to the n over n. When I simplify that 2 minus 3, I get a negative 1 to the n power over n. And that happens to be our alternating harmonic series, which we know converges. So I know my series converges when x equals 2. What about when x equals 4? We do the same thing. When x is 4, take that 4 and plug it into the original series. So I have 4 minus 3 to the n over n. When I simplify that, I get the series 1 to the n power, which is just 1 over n. That's our harmonic series. That diverges. So now I know that my original series, our power series, converges for x that are between 2 and 4, including 2, but not including 4. All right, so that wasn't too bad. Now we have a theorem about when these power series converge or diverge. So for a given power series, sum of Cn times x minus a to the n there are only 3 possibilities. First possibility is the series converges only when x is equal to a. That's the case where we always have some convergence because that's the sum of all zeros. Another possibility is the series converges for all x. And the last possibility is the situation that we already showed in the last example. It says there is a number r bigger than 0 such that the series converges if absolute value of x minus a is less than r, and it diverges if absolute value x minus a is bigger than r. And when x minus a in absolute values is exactly equal to r, you have to check those points individually. That was checking the endpoints like we did in the last example. So in all of these cases, we have something called a radius of convergence. So the number r in case 3 is called the radius of convergence. In case 1, that's where we just converged at one point when x equals a. We say the radius of convergence is r equals 0. And in case 2, where it converged for all x, the radius of convergence is infinite. So we have three possibilities for a radius of convergence. It's either equal to 0 when we converge only at one point, equal to infinity when it converges everywhere, or equal to a specific number r when it's one of those in-between states like what we had in that last example, where we have just a small interval for which our series converges. Now that interval is called the interval of convergence. The interval of convergence is the interval consisting of all values x for which the power series converges. And I'm just going to put one big note down here. Always test the endpoints. So when we're finding the radius of convergence and interval of convergence, if the radius of convergence is 0, the interval of convergence is a single point, x equals a. The radius of convergence is infinite, well then my interval of convergence is all real numbers, negative infinity to positive infinity. And if I get a radius of convergence r, then I have an interval of convergence like that last example where we had 2 to 4. But the important thing is in that last case, you always check the endpoints. Anything can happen at those endpoints. They can both be included in the interval, both excluded, or one included and one excluded. So you should check them every single time. Let's do another example of this, but now using our terminology since we know it. So let's find the radius of convergence and the interval of convergence of the series sum from 0 to infinity, negative 3 to the n, x to the n, square root of n plus 1 in the denominator. And again, we're going to use that ratio test for absolute convergence. So let's look at the limit as n goes to infinity of the absolute value of an plus 1 over an. When I plug in the n plus 1, I get negative 3 to the n plus 1, x to the n plus 1, and a square root of n plus 1, which is n plus 2. Now I'm going to multiply by the reciprocal of an, so I get a square root of n plus 1 over negative 3 to the n, x to the n. Now we should simplify this as much as we possibly can. Notice that with the negative 3 to the n plus 1 and negative 3 to the n, inside of absolute values, that would simplify to just a positive 3 in the numerator. I can simplify some of my x's, it'll be just an x in the numerator, but I need to keep it inside of absolute values because I don't know if it's positive or negative yet. And for the square roots, I can't cancel those out, but I can at least write it as one gigantic square root. So let me pull that absolute value of x to the outside. And I can actually pull that 3 to the outside as well. Then I just have a limit of the square root of n plus 1 over n plus 2 as n goes to infinity. So if I take that limit, this limit ends up being 1 So my actual answer is 3 absolute value of x. In order for this to converge, we want 3 absolute value of x to be less than 1. So if I solve that, we get absolute value of x is less than 1/3. And that means that negative 1/3 is less than x is less than 1/3. So I'm almost done now. We have our radius of convergence. My radius of convergence is 1/3. You have your radius of convergence as soon as you have it set up as absolute value is less than that number. And for the rest of this, I have to check my endpoints, negative 1/3 and positive 1/3, to see if they're included in my interval of convergence. So let's check those endpoints. If I use x as negative 1/3 and plug that into my original series, I'm going to have a negative 3 to the n and a negative 1/3 to the n, all over a square root of n plus 1. When I simplify this, negative 3 to the n times negative 1/3 to the n is a positive 1 to the n, or just a 1. So I have a sum from 0 to infinity of 1 over square root of n plus 1. And this is going to diverge. How do I know it diverges? Well, because it behaves like a p-series with p equals 1/2. And now when I check with x equals 1/3, plug that into the original series, I get negative 3 to the n, 1/3 to the n, over square root of n plus 1. This time, when I simplify my numerator, I get a negative 1 to the n power over a square root of n plus 1. So for that, I would use the alternating series test because it is an alternating series. Remember, the alternating series test said, check to see if we are decreasing and if the limit goes to 0. So first, check to see if my an plus 1 is less than an by checking if a 1 over square root of n plus 2, is that less than 1 over square root of n plus 1? And it is, because the square root of n plus 2 is larger than the square root of n plus 1, so dividing by it results in a smaller number. The other thing I have to check is if the limit of 1 over square root of n plus 1 as n goes to infinity, if that is 0. Well, it is, because the square root of a really huge number is staying really huge. 1 divided by a huge number goes to 0. So by the alternating series test, that series converges. So now I can write down what my interval of convergence is. We had before that our radius of convergence was 1/3, and the interval of convergence we said was between negative 1/3 and positive 1/3. And now we know with negative 1/3 we diverge, and with positive 1/3 we converge. So we have a parenthesis with negative 1/3 and a bracket on the positive 1/3 to get our interval of convergence. All right, so that wasn't too bad. Now, we said we were going to talk about radius or power series and Taylor series and MacLaurin series. And so far we've only talked about power series. So it's time to talk a little bit about Taylor series and MacLaurin series. But the good news is that in our previous video, we talked about Taylor and MacLaurin polynomials, and it's not a very big jump to get to Taylor and MacLaurin series from our polynomials. So let's have a definition. A series of the form sum from 0 to infinity, nth derivative of f at some value x0 over n factorial times x minus x0 to the n is called a Taylor series. For the function f of x about x equals x0, or centered at x0, same thing. So notice that this definition here is identical to the definition we had for a Taylor polynomial. The only difference is instead of going to just some number n, our sum's going all the way to infinity. So this is no longer a polynomial, but it acts very similar to a polynomial. It'd be like if you had infinitely many terms in your polynomial, which we can't have. But it's very similar. Our other definition is for a MacLaurin series, and it's really not that different either. The only difference is that MacLaurin series are centered at 0. So our MacLaurin series for f of x looks exactly like our MacLaurin polynomials. It's just it goes up to infinity instead of stopping at a certain point. So to finish up this video, we are going to find a MacLaurin series for a function and find its radius of convergence. And then we're going to find, I guess we'll find another MacLaurin series as well and find that radius of convergence too. So let's start by finding the MacLaurin series. For e to the x. And we're going to find its radius of convergence. Well, first, to find the MacLaurin series, we know that the MacLaurin series is going to look like a sum from 0 to infinity of the nth derivative of my function evaluated at 0 divided by n factorial times x to the n. So I need to figure out what the nth derivatives of my function look like at 0 so I can plug it into this formula. Well, luckily, the function e to the x, it's super easy to find all of its derivatives. F of x is e to the x, so I know f of 0 is e to the 0, which is 1. When I take a derivative, I still get e to the x. So evaluated at 0, it's still 1. It doesn't matter how many derivatives I take. Evaluated at 0, I'm still going to get 1. So that means to write my MacLaurin series, instead of having the nth derivative of f evaluated at 0, I plug in what that actually is. It's 1. So my series looks like 1 over n factorial times x to the n, which a lot of times we actually just write that as x to the n over n factorial, just because it looks a little prettier that way. So that is the MacLaurin series for e to the x. Then to find the radius of convergence, we have to use our ratio test for absolute convergence. So find the radius of convergence by using that ratio test. We have to look at the limit as n goes to infinity of my series with an n+1 plugged into it, divided by my series with n plugged into it. And again, I'm going to write that as multiplying by the reciprocal. So I have to evaluate this limit. Our factorials simplify nicely. I'm just going to have an n+1 left in the denominator. And my x's simplify nicely as an x in the numerator. I have to keep that x inside of the absolute values, but I'm going to pull it out in the front. So I have absolute value of x times the limit as n goes to infinity of 1 over n plus 1. Well, what's the limit of 1 over n plus 1 as my n gets larger and larger? Well, that goes to 0. So even with that absolute value of x there, I still get 0. And the important thing is this is less than 1 all the time, no matter what x was. So this means that it converges always. So that means my radius of convergence is infinite. All right, well, let's just do one more example. And we've done quite a few examples finding the radius of convergence now. So this last example, we're just going to find a MacLaurin series and then call it a day, because this MacLaurin series is a little bit more complicated. So let's find the MacLaurin series. For the function f of x equals sine of x. So we have to remember that in general, a MacLaurin series looks like a sum from 0 to infinity, nth derivative of our function evaluated at 0 over n factorial times x to the n. So in order to find the MacLaurin series, I need to start by finding a lot of derivatives of my function and evaluate them at 0. We do that until we've discerned some sort of pattern, and then we can use that pattern in this formula to write the MacLaurin series. So let's start by finding a bunch of derivatives of our function and evaluating at 0. My function was sine. So my function evaluated at 0 is sine of 0, which is 0. My first derivative is cosine of x. So when I evaluate that at 0, I get 1. My second derivative is negative sine of x. When I evaluate that at 0, I get 0. Third derivative is negative cosine of x. So my third derivative at 0 is negative 1. When I get to the fourth derivative, I get back to my original function, sine, and my fourth derivative at 0 is back to 0. So I can look at my derivatives over there, and I see that I'm always going to be 0, 1, or negative 1. If I were to write out all of the terms in this series, all of the ones that have a 0 for that derivative, they're not even going to show up because they're multiplied by 0. I'm only concerned with the ones that are 1 or negative 1. I know it's going to be alternating, and I also know that it's occurring at the odd derivatives. I have the first derivative and the third derivative. My fifth derivative will be positive 1. My seventh derivative will be negative 1. So I need to find a way to just write the odd derivatives. So let's notice that we only need odd derivatives / powers in our series. And we know that a way to write an odd number we can write an odd number as 2n plus 1, where n is 0, 1, 2, and so on. Because if I plug in 0, I get 1. If I plug in 1, I get 3. Plug in 2, I get 5, and so on. This will get me just my odd numbers. So I know that if I look at my MacLaurin series, I need alternating powers or alternating signs. I'm leaving that power unknown right now. We'll figure out if it should be an n or an n plus 1 or what's going on up there at the end. But I'm going to have a -1 to a power from my derivative. I'm going to have the factorial in the denominator, but I only need the odds. So it's going to be 2n plus 1 factorial. And then I have my x to the 2n plus 1 power because I only need the odd powers. So I use that 2n plus 1 to indicate that we're just going to get odds there. And now I just have to figure out the power on this -1. My first derivative, which occurs when my n is equal to 0, is going to be positive. So I can just put an n here because when I plug in that 0, I get positive. And then my next derivative that's represented in this is negative. When I plug in the n equals 1, I'll get a negative. So this is how I'd write the MacLaurin series for sine. Now, we are out of time for today, but I'm going to quickly write down for you what the MacLaurin series for cosine looks like, so you can try it on your own and see if you get the right answer. The MacLaurin series for cosine looks like a sum from 0 to infinity, -1 to the n, over 2n factorial, x to the 2n power. So on your own, you can try to find that MacLaurin series for cosine and see if you get this as a result. That'll be a good test to see if you're understanding how to do these. And that is about it for today. We will be continuing with more information involving our Taylor and MacLaurin series, including other operations we can do with these series. And it's going to get pretty cool. So I hope you continue watching the videos. If you have a question for me, feel free to ask, and I will see you the next time.